Welcome to the world of EYYES. My name is Wolfgang Domann. I'm Managing Director of EYYES and I'm happy to talk today about the essentials of driving assistance systems based on deep learning. Some introduction first. We from EYYES have the vision to protect the world of tomorrow with AI. So everything of our products and solutions is turning around safety. Our motto is we make machines see. So we have the sensors to detect every kind of object around vehicles. And our experts are experts in AI, in computer vision, deep learning and embedded systems. And we do in addition also software development and also our own hardware development to create tailor-made products and solutions. We are around 35 people in 3 locations in Germany and in Austria. We have been founded in 2013 and we are the leading technology provider for AI-enabled platforms on the edge. We have here a complete stack of technology. We have some products which are ready to run and can be bought in the aftermarket. These are driving assistance products with a defined function, for instance a blind spot assistant or a rear view assistant, and these systems can be mounted on every vehicle. They have an ABE, they are certified, and our blind spot assistant has been approved in a competition last year in August against 8 other systems from ADAC, the German Automotive Association, as the best blind spot system available in the market. And why? Why? Because we are the only system who has already deep learning integrated, and this makes the system for the driver much more convenient because we have with our system the minimum false positives signals for the driver. This means that it's for the driver the best usable way to deal with this driving assistance and he gets no false alarms. Our rear view assistant is based on the same technology and we have also a moving off assistant who is looking in the front. And what we bring on the market this year is a 270-degree assistant for construction vehicles, where you can see on the left, right or back side of the vehicle, and we detect then pedestrians and objects to prevent all of the vulnerable users which are around the vehicle, or we can use the front, left and right side. But how do we come to a complete driving assistance solution? Because for these products we are our own client, so to say. We are using all of our technology stack to provide these products. And we have also in railway a front collision assistant, which is close to the systems in the utility vehicles, but with some different requirements from the client. And we have also upcoming systems for coupling monitoring and for blind spot assistant also in the railway market. What are the necessary ingredients for an ADAC product and solution? So at first you need of course the sensor. In our case it's mainly camera sensor based, and I will come to the difference between camera sensor and radar sensor later on. Second, you need a special trained deep neural network which can be used for traffic situation. And the better a neural network is detecting the objects, the better the quality of the driving assistance system is. And you need the full software to process the image and process the AI. And of course, the end user know-how, what is the expectation of a driver to this system, which is highly connected also to the regulations and the regulation know-how what the system has to achieve to get an official certification from TÜV or KBA or any other certifying organization. And last but not least, you need a performant hardware which can calculate this AI. And the major issue is that the central ECU and the processing power is driving the cost of a driving assistance system. Coming to the first point, starting with the sensors. So we have in the moment two options which are cost efficient and available. We have radar sensors and we have camera sensors. And the optical frequency of the light is from 300 to 800 nanometer, and the wavelength from radar is 3 to 67 centimeter. And what is the difference? So the difference is, of course, that the optical sensor has a much higher possibility and accuracy to classify and detect objects. So the visual sensor is here in an advantage, of course. The disadvantage is that optical sensors are indirect, so you need some light, and without any light which is going to be reflected, it's not working. The radar sensor is an independent sensor because it's an active transmitter, so it's independent from any light or daytime situation, and the reflection of the radar under bad weather condition is still working. So here there are also some advantages compared with the optical sensor. And today it's the case that especially in utility vehicles, in trucks and in buses and all other vehicles, till today the radar sensor was the prime sensor for all kind of assistance systems. And this is changing now because we need more intelligence. We have a higher expectation on safety, a higher expectation to the robustness and to the quality and the use cases which are expected from the users. And now the camera is moving into the first sensor row of object detection. So the camera is now the prime sensor, and the radar is mainly used as second sensor to be sure that you can rely on, or to be sure if you execute an active braking that there is really an object coming in front. So if we put the things together, we have in the camera the higher resolution, we have the more detailed information, we have a longer distance because the radars which we can use at the moment, due to the width of the radar stream, have a much shorter distance. And the only advantage of the radar is, of course, they are robust and weather independent. But if we move, so to say, the priority, camera will move to priority 1 based on deep learning, and the radar will move as a sensor to priority 2. Coming to the second topic, the neural network. We have with IceNet a pre-trained neural network which we trained over the last 5 years for all kind of traffic purposes to detect objects and classify objects. You can see here a scene in Vienna in the city on the right side and in the underground on the left side to detect pedestrians and objects on the street. The major topic is the better the detection quality of the CNN is, the better is the quality of the driving assistance system. So it's the foundation or the base. Without any good trained CNN, the system will not work properly. And based on this CNN, you get then with the sensors as result a real-time streaming of object data image quality analysis, and a 2D 3D estimation about the distance of the object. And we can classify, of course, into the classes of pedestrians, bikers, cars, trucks, traffic lights, traffic signs, and also lane recognition is possible. But how come and how does it work to get to such a CNN? So here you can see the development process, and we have the right to gather video data on the street. So over the last years we gathered a lot of traffic situations which we have as a source. After the gathering of data, we have invented a big machine for auto annotation of data. So this is automatically done. There is no manual work necessary and needed. And after the auto annotation, we use, of course, the data for training of the CNN to evaluate the CNN model. And we have some own patented tools then to improve the CNN, so for the quantization, pruning and optimization, to get an optimized model, which is then be used we export it, so to say, as file, which can then be deployed on the hardware. And the importance is that we have a model which is optimized by factor 40 compared to the original model. So we need a maximum 5% at the moment of calculation power of the original model to achieve the same object detection result. So this is the first big optimization step before you put the model into the AI inference engine at the hardware. Coming to the full technology stack, which is behind, we talked about the IceNet on the first level and the CNN. The second level is the use case software. We have a framework with about 120 C++ modules, and every developer can take these modules and put it together in sequence or in parallel, so he can compose his use case without any development efforts. So this makes it happen that every driving assistance use case can be put together with this composer in a very short time. So everybody who wants to develop a product can use our CNN, or he can take his own CNN, he can use our modules, put them in the right sequence and configure them to get a proper runtime software, which can then be put on the hardware level to be executed on the edge. And we are fully hardware agnostic on this stage. So it can be used on a GPU hardware, or it can be used on our hardware, of course, because we have also our own AI accelerator, which is based on AMD Xilinx FPGA at the moment, and we have a system on module which we call real-time interface, and this is our AI processing module, which is provided in our hardware boxes as AI calculator. And in our products, which you have seen at the beginning, the aftermarket products, we are using this full stack of technology, our neural net, the software framework, and the hardware with the AI inference engine together to have a complete product. And we can do, of course, the same for anybody else to compose a new driving assistance solution. Coming to the use cases, so what is the outcome if you use the CNN and the software framework? And I brought here also an example with me. So what you can see here is the use case test of our front collision assistant. You can see the video, the detected objects. You can see the track recognition, so that we predict where the object is moving and going to, and we are calculating now the time to collision, and when the object is trying to hit us, we can give out an alarm signal, and this is exactly what's then the result or output of the runtime software when you put it together as a front collision system. And in addition, just that you see, we have now added the camera-based sensor with the radar sensors. So what you have seen now was the camera, and now you see, so to say, the video again with including the radar sensors. And here we get the robustness and the additional perception that if we give out a warning that there's a real issue that a car wants to hit us. So we can see here also the two radar results on the vehicle in the screen. So putting this all together, we can provide a complete software platform that we can execute all driving assistance functions needed in a truck or in a bus. So this is what we strongly believe, that it's not about only making one function like blind spot or rear view or voice. It's about having all of these functions in one system. So with one software platform, having a front collision warning, a moving off assistant, a rear view and rear collision warning, adaptive cruise control, a lane keeping assistant, a blind spot assistant, and a cross traffic alert on the front and the back side if we integrate all of the radar sensors as well. So we need 7 to 8 cameras around the vehicle, and the radar sensors, we connect them to one box, and at the end you get a full driving assistance solutions out of one hand with a software which is already tested and proven from ADAC with a lot of experience in the EU regulations and requirements know-how for the utility vehicle market. And we have, of course, also the functional safety experience, because we are dealing for several years in the rail market and now also in the automotive market. So it's one platform out of one hand. We deliver the intelligence to your products. We can provide the software platform, the CNN on top, and we can then provide the hardware. We can develop the ECU with you together, but the full scope of requirements engineering, the design of the product, product development, and the support we can provide, that you come to a better vehicle at the end. So thank you very much for your attention, and happy to have some discussion further on. Thank you.